All right, what's up, VL AP Statistics students? This is Mr. Bachman here. We are going to work through our Week 3, Day 2 lesson. We're moving into Unit 7 today, and our topic is the t-interval for mu. All right, so quick agenda. I'm just going to give you a little information about the assessment that I'm assigning today. We're going to run through the next row of the inferences for proportions, review grid. We'll do a question of the day. I'll talk a little bit about the confidence interval for a population mean, or the t-interval for mu. And then we'll wrap up at the end. All right, so a couple quick things about the Unit 6 assessment. This is the first assessment of Quarter 4. It is Schoology based. It's going to be 50 summative assessment points. I did put a 90-minute limit on there. You probably won't need that amount of time, full amount of time, but you do have 90 minutes. It's due, actually, I'm sorry, I just changed this. It's going to be due on Friday, May 7th at 10 a.m. Sorry about that. The material that I'll be covered, it's basically three main topics. It's the z-test for P, type 1 and type 2 errors, and then the z-test for P1 minus P2. So it doesn't have any confidence interval material on it. It's all significance tests. And then you can see, if you want to review some of those AP classroom videos, here are the AP topic numbers. The format of the assessment, there'll be 6 to 8 multiple choice questions. And then there will be one 4-step problem. You're going to do it on paper, take a photo, and then you're going to submit it to the Schoology problem. So that's how you complete that one. There's just one of those 4-step problems. So I want you to be ready for that. And then that one will be weighted quite a bit more heavier than each of the multiple choice questions. Okay, so again, that's due Friday, May 7th, 10 a.m., and that is on Schoology. It is available to you now. It's in the Week 3 folder. Okay, next up, we're going to go through our inferences for proportions review grid. This will be on we're going to do the bottom row there, the 2 sample z-test for P1 minus P2, and summarize this stuff from the Day 1 lesson. So this is what you have here. This is available in Schoology. Again, we're going to be doing this row. Okay, so we're going to start with the purpose. So the purpose of the 2 sample z-test for P1 minus P2 is to test a hypothesized difference between 2 population proportions. So I'll say population proportions. Right, so we're making a hypothesis about 2 population proportions, and we're specifically looking at the difference between the two, so kind of using subtraction there. Okay, so the next column there is conditions. So for this, we have some conditions that need to be met. So we need 2 independent random samples. All right, so 2 independent random samples. You need, remember, the 10% rule for each sample. So remember, that's the sample size can be no larger than 10% of the population. That ensures that you have independent independent samples. And then remember, all of these, n1 times p hat 1 needs to be greater than or equal to 10. We need n1 times 1 minus p hat 1 needs to be greater than or equal to 10. And then the same thing for the second. n2 times p hat 2 greater than or equal to 10. And n2 times 1 minus p hat 2 greater than or equal to 10. All right, so those are the conditions that must be met before you can do your z-test, your significance test. Next up is the test statistic, and that's a z-score. And kind of a big formula here. So it's p hat 1 minus p hat 2. So that's the difference of your two sample proportions, minus P1 minus P2. This, remember, is usually 0. So that's almost always going to be 0 right there. And then the standard error, big formula, is big square root. And remember, what we have to use here is our combined sample proportion times 1 minus that combined sample proportion over N1 plus, and then P hat sub C, and then same numerator over N2. So that's going to give you that test statistic of Z. And then just so you remember, I'll put this down here. Remember, our combined sample proportions is X1 plus X2 over N1 plus N2. Again, that's going to give you your combined sample proportion. Okay, and then how to calculate a p-value. Again, that's normal CDF, just like we've always done. And then the calculator trick, I'll show you how to use this in a sec, but it's 2 prop z test. So 2 prop z test. All right, I'll show you that right now. I'm going to pull up my calculator. So to access 2 prop z test, you hit the stat button, you go over to tests, go down to 2 prop z test, hit enter. It asks you for x1, n1, x2, n2, and then a place to put your alternate hypothesis, and then you have a calculate option and a draw option. So let's go ahead and use the example from the day 1 lesson where we were looking at the proportion of black respondents that supported DC statehood and then the proportion of white respondents. So if you remember that example, there was 151 out of 253 black respondents in the sample that favored DC statehood, and there were 602 out of 1,611 white respondents that supported DC statehood. And we were trying to show that the first population proportion was greater than the second population, so that the black population proportion was greater than the white population proportion. So I'm going to select my greater than alternate hypothesis. Then I'm going to go down to calculate and hit enter. And then you can see that we have very similar z-score and p-value to what we had when we did this, when I did this problem in the last video. You'll also see that it also has the combined sample proportion, that that 0.404 number right here. It gives it to you just as p hat. We notate it as p hat sub c, but that's going to be your combined sample proportion. So again, up here we have the z-score and the p-value. So z-score about 6.7, p-value about 8.8 times 10 to the negative 12th, again, which is very similar to the values that we got in that last video. So that's how you use 2 prop z test. All right. So at this point, you should have this inference grid filled out, and it should be a good resource for you as we're moving along here. Okay. We're going to move into now the question of the day. This is in Schoology as the week 3, day 2 Ignite. So make sure that you get your answer in here into Schoology. So it says, today we'll be making confidence intervals for a population mean. So let's review making a confidence interval for a population proportion. Again, we're using that same context that I just addressed. We're just, in this case, just concerned about the p-hat value for the black respondents. So from the poll, 151 out of 253, so again, about 59.7% of black respondents answered either strongly support or somewhat support regarding DC statehood. Make a 95% confidence interval for the proportion of the black population that supports DC statehood. So this one, you don't have to do all 4 steps, just actually calculate the interval. So if you want to just take a moment, pause the video, and work through how to find your interval. And then you can check back and I'll have the solution. And I'll go through the solution with you. Okay, so again, pause the video, do the problem, submit it to Schoology, and then come back for the answer. Okay, welcome back. All right, so here's the formula for the confidence interval. So remember that p hat is that 0.9 or 597 from the survey. The n value was 253. And the only other thing we need to put in there, remember, is that critical z-score. And that, remember, comes from your confidence level, so that 95% confidence. So remember that in order to get that number, you go to your calculator, and you're going to use the inverse norm function. And I will show that to you again right now. So inverse norm, remember, is second vars, and then inverse norm. And then it's going to ask you for an area, and then a mean and a standard deviation. So remember, what we put in for area when we're trying to find that critical z-score is the left area. It's the tail probability, so the left area, so the area to the left of that middle 95%. So the critical value, or the tail probability of 95% confidence is 0.025. We're going to leave the mean and standard deviation as 0 and 1, keep it as left, and then hit enter. And you get that z-score of about 1.96 that we've seen lots of times. So that critical z-value is 1.96. I'm going to put it as positive because in the confidence interval I'm doing plus or minus. Okay, so now I'm ready to put everything into my formula. So 0.597 plus or minus that critical z-value of 1.96 times, and then I'm going to put in my numbers into the standard deviation, and n is 253. All right, so then what I can do is I can put this whole margin of error into my calculator. So you probably did that. I got 0.06, so about a 6 percentage point margin of error. And then my point estimate again was about 0.6. And then if I actually calculate my interval by doing that adding and subtracting, I get 0.537 to 0.657. So that would be my confidence interval. That would be the estimate that I would use to, that would be the interval that I would use to estimate the true proportion of black voters who support DC statehood. So about 53.7% to about 65.7%. Okay, hopefully you got that answer. So again, make sure that you get that submitted to Schoology. And what we're going to be doing now is moving into how do we do this confidence interval process for a mean, right? So we've done it a lot. We've done a lot with proportions, and we're moving back into means. Okay, so I'm going to keep going with my slides here. So we've estimated P by calculating a confidence interval using a sample proportion. That's exactly what we just did there. But now we need a way to estimate mu. Remember, mu is a population mean. So it could be parameters like the average weight of NFL football players, the average gambling winnings of Las Vegas tourists, or the average age of American voters. All of those things, it's going to be really challenging to actually calculate the mean. You could probably do it with the NFL football players example, but it'd be nearly impossible to actually calculate the average age of American voters or the average gambling winnings of Las Vegas tourists, just because those population sizes are so large. So we're going to go through a process on how to do that estimation technique using just a sample. All right, so a couple goals for today. We're going to learn how to find a z-interval for mu, and then the four-step process. And then we're going to learn how to find what we call a t-interval for mu. So that's a little bit so it's a different kind of interval, a t-interval. We're going to learn about the t-distribution today, and then we're going to learn a four-step process to go with it. All right, so let's just jump right into the 4 steps for calculating a z confidence interval for mu. This is when the population standard deviation is known. So this is actually not a very practical process Because if you're doing a confidence interval for mu, it means you don't know what mu is. If you don't know what the population mean is, you're probably not going to know what the population standard deviation is. So we're really not going to use this process much, but this will help us set up our more practical process, which is the t-interval. Okay, so step one, you're going to identify that parameter of interest like we have been doing. So that is your step one. Step two, and also in step one, we're going to name the procedure. Proceed. Yeah, that's okay. All right, so usually we're going to do, I put this in step two. We've been putting it in step one, so I'm just going to draw a little arrow there. Step two, then, we verify your conditions. So the sample was randomly obtained, okay, just like, we always have that condition. Second condition, sample size less than 10% of the population. Again, we always have that 10% rule. And then we also need some information about to make sure that we have both a normal and a large enough, but we have a large enough sample to justify a normal distribution. So if you remember back to when we were doing sampling distributions for X bar, we had the central limit theorem. So the central limit theorem, CLT, remember, is that if you have a large enough sample, you're going to have a normal sampling distribution. And that generally occurs when n is greater than or equal to 30. So that's a quick one you can always check. Is that sample greater than 30? If it is, you know that central limit theorem is going to be met and that you're going to have a normal sampling distribution. Another way, though, to justify the use of a normal sampling distribution is that the population is known to have a normal distribution. So again, these are OR, so both of them don't need to be met. We just need one or the other. And then there's actually a third way to do it, and the third way to do it is if you have no strong skew or outliers in the sample data. And a lot of times we'll do that by either making a dot plot or making a box plot. If we're using our calculator, it's pretty fast to make box plots on our calculator, so that's usually the way we're going to do that. And then, as I mentioned, the population standard deviation has to be known in order to use this process. Okay, so that's step two. Step three is where we carry out our procedure, and this is the formula for a confidence interval for mu. So we just did a confidence interval for P, and that was this formula here. It was P hat plus or minus Z times that standard deviation or that standard error. Well, we're going to do the same thing down here. It's your point estimate, and this time, though, it's X bar. So instead of proportions, this will be means, so it could be really any kind of number. It's not always just going to be a decimal value. Z, well, that's the same critical Z score that comes from inverse norm. And then here is our standard deviation, sigma over the square root of n. We've seen that formula again in our sampling distribution unit that we had several weeks ago. And then the last step is you're going to interpret your results in the context of the problem. If you remember back with our confidence intervals, you say like, I am 95% confident the interval blank to blank captures the true and then whatever you're estimating. And that's what you do in step four. Okay, so now the big question is okay, well, what if sigma is not known? And it's almost always not known. So as I said, this process isn't super practical, again, because usually we don't know that sigma value. All right, so in practice, if the population standard deviation is not, in practice, the population standard deviation is not known. If it was, it would imply that you knew the population mean, and the confidence interval would be somewhat unnecessary. So to calculate a confidence interval where sigma is unknown means we need to learn a new type of distribution. All right. So again, since we don't know the population standard deviation sigma, we can no longer rely on the normal distribution for our calculations. So we can't use the normal distribution, we can't use z-scores here because, again, we don't know sigma. Thankfully, William Seeley Gossett solved that problem for us. So here is a little mini history lesson. So again, his name was William Seeley Gossett. He wasn't, so he's since passed away, but really not that long ago, if we think about kind of how long all of this stuff has been going on here. So He was an immensely talented statistician to be remembered for his contributions to the development of modern statistics. Better known to the statistical world by the pseudonym Student. So he didn't publish his work in his own name. He used the pseudonym Student. Gauss's name is associated with the discovery of the T-distribution and its use. So he was a brewer at Guinness Brewery in Dublin, which is in Ireland, and the pioneer of the analysis of small samples. His most famous work, The Probable Error of a Mean, published in Biometrica. So there's his article right there. Made a clear distinction between population parameters and sample estimates of them, right? So again, we don't know sigma. We want to be able to use S, our sample standard deviation, instead. So he'll be remembered for as a practical scientist for his discoveries of the frequency distribution of the variance of normal samples and the ratio of the mean to the standard deviation in the theory of statistics. His life was one full of fruitful scientific ideas, and Student's test of significance finds a unique place in the history of the scientific method. So just a little information for you there. We're going to eventually get to the his test of significance. Today we're doing his confidence interval, but it all kind of comes from this. Well, how do we deal with this relationship between sigma and S? Okay, so I'm going to give you a little information about this T-distribution. So if the population standard deviation is unknown, we must estimate it using a sample standard deviation. Again, that's S. The value of S may not be close to sigma, especially if n is small. So further, S may vary from sample to sample. As a result, the use of S in place of sigma introduces extra variability into our problem, right? So like what we would want to do here is it would be nice if we could just put S in place of sigma, but S isn't as good an estimator as it should be for sigma. So what we can then no longer rely on Z as an appropriate thing there. Okay, so due to the extra variability, the T-distribution is more spread out than the normal distribution or the Z distribution. So if you go into the slides, there is a link here. You can play with this little applet, but I'm going to show you this now. So I'm going to pop this up. All right, so what I have here are two distributions. The red distribution here is the normal distribution, so the one that we're used to using. And then the T-distribution is this dotted blue one. We can see right now it is more spread out. But the T-distribution relies on the sample size and a new calculation which we call degrees of freedom. So degrees of freedom, it's a pretty simple formula. It's just the sample size minus 1, or n minus 1. So if we have a sample size of 50, we have 49 degrees of freedom. If we have a sample size of 9, we have 8 degrees of freedom. And the number of degrees of freedom in your sample affects the mainly the spread of the T-distribution. So I have a little slider here, and what I can do is I can move this slider, and that's going to change my distribution. So I can see if I only have 1 degree of freedom, a sample size of 2, we can see that this T-distribution is more spread out than the normal distribution. As I increase my degrees of freedom, right, I can see that it gets closer and closer to that normal distribution. And it doesn't really take that, it doesn't take a huge sample to do that, right? And I can see if I have 29 degrees of freedom, right, that'd be a sample size of 30. That's almost normal, right? So, but we can see it's quite a bit different if we use a really small sample size. All right, but we can see that the shape of the T-distribution does have that bell shape, but again, it's just a little bit more spread out than the normal distribution, and it depends on the sample size and the degrees of freedom. All right, so a couple things we just saw here. The T-curve is bell-shaped and centered at 0, just like the Z-curve. Each T-curve is based on the number of degrees of freedom, so df equals n minus 1. Each T-curve is more spread out than the Z-curve, right? We also just saw that. As the number of degrees of freedom increases, the spread of the t-curve decreases. So as the df increases, we could see that it did get less spread out. And as the number of the degrees of freedom increases, the corresponding sequence of t-curves approach the z-curve or the normal distribution. So that we saw that as well. So just kind of a little bit of summary there. Okay, so now how does that then show up in our confidence interval? So recall that z-scores, critical z-scores, were found using the confidence level and the inverse norm calculator function. So we looked at that when we just did our Ignite. But now critical values are found using inverse t. And inverse t has two arguments. The first argument of inverse t is that same tail probability of the confidence level. Right, so when we did 95% confidence for the z critical value, we used 0.025. So that's the 2.5% on each tail of that middle 90%. And the second argument is simply your degrees of freedom, so n minus 1. So those are the two things that you put into inverse t. And again, critical t values are based on the confidence level and the corresponding tail probability, and then the degrees of freedom from the sample. So if we're trying to figure out what is our critical t value for, let's say, 95% confidence and let's say a sample size of 20. So if the sample size is 20, we have 19 degrees of freedom. So we know that our critical z-score for 95% confidence is 1.96. So let's see what the critical t value is for this scenario. So I'm going to go back to my calculator. So now I'm going to use inverse t. So that's second vars. And I go down. Inverse t is right there. So the fourth option. I'm going to hit enter on inverse t. The area, I'm going to type in 0.025. That's that tail probability. And I had a sample, I said let's check it for a sample size of 20. So that's going to have 19 degrees of freedom. So if I hit paste and then enter, that's going to give me a critical value of about 2.093. So pretty close to that 1.96, but a little bit different. So for that, I would say, okay, that critical value is 2.093. So again, that's that critical value. Sometimes you'll see that as T star. So I'll kind of show you then in a minute where that shows up then when we're going through our procedure here. Okay, so now let's look at the 4 steps for calculating that T confidence interval for mu. So now this again is where S must be used. Okay, so remember for step 1, so you're going to identify that parameter of interest and you're going to name your procedure. So the procedure here again, I call it the T interval for mu. And then in step 2, you're going to verify your conditions. So sample was random, 10% rule. Again, this is that large sample normal condition. So either n is greater than or equal to 30 by the central limit theorem. Population is known to be normal, or no strong skew or outliers. So usually that's done by just graphing the data using either a box plot or a dot plot. And then the population standard deviation sigma is unknown. So in this case, remember this is when you're using S. So if you know S from that sample, you're going to be using this T interval. Okay, so then what happens is this now is our new confidence interval formula. So notice that instead of Z, we have T. That's that critical T value, which comes from inverse T. And then I can see that I'm using S there instead of sigma. So it's X bar plus or minus T times S over the square root of N. So again, X bar is what we call the point estimate. And then everything after the plus or minus sign, right, is our margin of error. So once you have that, then you interpret your results in the context of the problem. So I am blank percent confident the interval blank to blank captures the true mean and then of whatever you're measuring. Okay, so that would be step 4. So that basically gives you your 4-step process for the t interval for mu. I'm not going to do a full example in this video. When we get into week 4, I'll do an example where we put this all together. But really, I just wanted to show you the 4-step process, talk a little bit about the t distribution, and then kind of see where they all connect. Okay, so asynchronous work. This is the same as what I had in the day 1 video. These problems you already know how to do from the week 3 day 1 lesson. Now you are able to do these problems. Notice I don't have any 4-step problems in this page 664 section. The 4-step problems for the t interval for mu will come next week. Okay, and then these videos here are AP Classroom videos. Those cover what you all learned in the day 1 lesson. And then if you need a little more information about the t distribution, this 7.2 daily video 1 is a good one to watch. Okay, I think that's all I have for you. Shoot me an email if you do have any questions, comments, concerns, things like that. Otherwise, good luck with your work this week, and I hope you have a great day. Bye, everybody.